so this example problem is going to have 4 parts, parts A through D. And so for part A, what we're doing is we're going to find the bending stresses at these points. Okay, so it's at x is equal to 0, so it's at the wall here. And it's at 2513, which means it's in the y direction is 25, which is just like the top surface here. Whoops. And the 13 is, I think this is, what is this? This is 26 millimeters wide. So this would be this top surface here. And then we have at, it also asks us to find the stress at the bottom point here. All right, so this is for A. That's what we're going to do. The second part of the problem asks us to find where is the neutral axis and the points undergoing the maximum and minimum bending stresses. Okay, so our neutral axis is our angle beta, right? And that would be from, so we're not sure which way it's going. It could be going either way, but that's what we're looking to solve for here. So which way is the angle going? Is it going this way or this way? So our neutral axis is going to go along this way, or is it going to go along this way? All right. So once we locate our neutral axis, we should be able to identify the locations of our maximum and minimum bending stresses. They're going to be the points that are going to be furthest from our neutral axis. Once we do that, we can then use the direct method to find. We're going to use the direct method to find the neutral axis. So I guess I should say earlier we were solving for alpha, and then we were solving for theta p to determine where our neutral axis is. And then in part C, we're just going to use the direct method to find beta. Beta is just equal to alpha plus theta p. Okay, so once we have those two, the last part of the problem asks us that we're going to just find the deflection within the x and y components of our at the end of our beam. So we just want to figure out what is delta x, delta y, delta z at the end of our. So this should be y and z, not x and y. Okay. So once we then we want to find what is the maximum value. Okay. All right. So are there any questions about the setup of the problem and what the problem is asking? Okay. All right. So the first thing, we're going to find the bending. We want to find the bending stresses at these 2 points. Okay. So to determine the stress at these points, we need to know the stresses my, mz, iy. We need to know the bending moments my and mz. We need to know what is the moment of inertia is about the yz and iyz axis, and we need to know y and z. What we're going to do is we're going to convert all these values from our yz coordinate system to our m n coordinate system, where m and n are our principal axes. All right. So from the problem diagram, we were given that there is a load of 2 kilonewtons that's applied along the negative y-axis. Right. That's going to create a bending moment that would be equal to about the z-axis. That would be equal to the force of 2 kilonewtons. All right. Times 750 millimeters. Okay, so that would create a negative moment of about the negative z-axis. So we have to include a negative sign. All right, so that's where we get these values here, and then once we have so those are our moments about the y and the z axes. So the next things we need to calculate is we need to calculate what is IY. So for IY, we can break up. So this is going to be like a review of statics. We can break up our cross-sectional area into 3 different parts. So we're going to have we have area 1, then we're going to have areas 2, and area 3. Okay, so for area 1, we know using the parallel axis theorem, we can calculate the moment of inertia about the y-axis. So it'd be equal to 1/12 times the base. So the base of our system is going to be equal to 50 millimeters. And then the height of our system is going to be equal to 10 millimeters. I'm going to cube that, and then our area would be just equal to 10 millimeters times 50 millimeters. But the distance between the centroid of area 1 and the y-axis is going to be 0. So this term on the right-hand side is going to be equal to 0, and we're left with just this term here. So what we end up getting is I of y1 is going to be equal to 4.166 times 10 to the third millimeters to the fourth. Does anyone have any questions about how I1y was determined? Okay. All right. So for I2, so you can do the same process for I2y. So I2y is going to be equal to 1/12. The base of I2 is going to be equal to from the last page is equal to 15 millimeters. So if we go back here, is equal to 15 millimeters, and the height of it is going to be equal to 8 millimeters. So we just have 15 millimeters. All right. So question, I'm just going to get through this line, and then I'll go back. And then we have 8 millimeters cubed for the height, and then we're going to get the area of the cross section is going to be 15 millimeters times 8 millimeters, and then the distance from the neutral axis y to the centroid of area 2 is going to be equal to 9 millimeters squared. All right. So Nikki asked about. She asked about where does the 0 come from in I1y, and then I think Sterling answers is the distance from area 1 from the centroid. So if we look at area, so Sterling is absolutely right here. It's the distance. So the distance d here is from the y-axis to the centroid of area 1. Now the centroid of area 1 lies on the y-axis. So the distance between the y-axis and the centroid of area 1 would be equal to 0. All right. For the second area, I2, that distance from the y-axis to the centroid of 2 is equal to 9 millimeters. Now, for simplicity, this is also provided. This is also provided here in this chart on the bottom page here. But if you were given the dimensions of the cross-sectional area, you'd be expected to be able to break the system down into the different smaller areas and then solve for the moment of inertia for each of the individual areas. All right. Cool. All right, so So if you solved for that, if you plugged in all those numbers, what you'd end up getting is you get I2 of y is be equal to I3 of y, which would be equal to 10,360 millimeters to the fourth. Right? So from that, IY would be equal to 24.9 times 10 to the third millimeters to the fourth. Okay? So we just have to add up I1 plus I2 plus I3y to get this value. Okay? So I'm not going to go through it, but you'd follow the similar procedure for finding I of z. So you would need to find IZ for point one for area 1, for area 2 and area 3. And if you repeat that process, you would get for IZ, you get 182.2 times 10 to the third millimeters to the fourth. Okay. All right. All right. So the last part of this uh, of the whatchamacallit, of the last thing that we need to solve for in terms of our the terms on the top left here is we needed to solve for I of z here. We also do need to solve for y and z, but well, actually, sorry, y and z were given to us. These are y and z. All right, so we just need to solve for I, y, z. So we're gonna do that on the next page. You can solve for I, y, z. All right, so I, y, z is gonna be, we can set sorry. All right, so to determine z, we can use this following formula for I guess for a composite section like we have here. So um, so in nearly every case, this IYZ term we're going to treat as 0. All right. So what ends up happening is we only really care about the term on the right here for to calculate IYZ. Right. So for our same cross-sectional area, I1 of Z, I1Y of Z, it'd be equal to solve for it, equal to the IYZ bar is going to be equal to 0 plus y times z. So y and z in this case is both equal. So this is again the distance from the y-axis to the centroid, distance from the z-axis to the centroid would both be 0 in this case. The cross-sectional area doesn't really matter here. So we can let it go. So the next, so we end up getting that I1 YZ is equal to 0. I2 of Y is going to be equal to IYZ plus YZ times A. So again, for IYZ prime, and then YZ times A, we're going to get it's going to be equal to 9 millimeters for the distance between the y-axis and the centroid. Actually, the centroid, and then we have 17.5 for z. And then our area is going to be equal to 8 millimeters times 15 millimeters. And that's going to be equal to, so if we multiply that all out, we get 18,900 millimeters to the fourth. Right. Then I have a question about where any of these numbers came from. Okay. If there's no questions, we'll go on to I3y. So again, I1, IYZ is going to be 0. And then we're going to be left with YZ times A. So in this case, our Y and Z are going to be negative. So we get minus 9 millimeters times minus 17.5 millimeters. And our area terms this will be the same. So it'll be 8 millimeters and 15 millimeters. All right, so we'll get the same answer of 18,900 millimeters to the fourth. So our IYZ would give us 37.8 times 10 to the third millimeters to the fourth. Okay. All right. So now we have now that we have IYZ, we can calculate our principal angle, theta p. All right. So all we're going to do is we're going to plug in our IYZ term, our IZ term, and our IY term, which we solved for on the last page and this page. If we plug in all those values, what we end up getting is we get 12.84 degrees, which is going to be counterclockwise from the y-axis. All right. So what this means is that if we have our y and our z, our y and our z, our principal axis is going to be 12.84 degrees from our m-axis, and our n-axis is going to be 12.84 degrees from our y-axis. Okay. So once we have theta p, we can then plug in our values of IY, IZ, and IYZ into the following equations to solve for IM and IN. So if we do that, all right, so we're just plugging in the values, and we have theta p as well. So we're just plugging in these values, just some algebra that you have to go through. If you do that, you would get 1.627 times 10 to the fourth millimeters to the fourth. And then for IN, we would get 1.91 times 10 to the fifth millimeters to the fourth. Okay. So the last thing that we need to solve for is we need to solve for our bending moments in about the M and the N axis. So if we go to the next page, all right, from the original problem statement, we were given these were our loads. We were told that there was no force about the z-axis, so the bending moment about the y-axis would be 0. And the moment about the z-axis we were able to calculate as minus 1.5 kilonewton meters. So using this information, we can then solve for m, the moment about the m-axis, the moment of the n-axis, using the transformation equations. So we plug in my is 0. We plug in mz is equal to minus 1.5. And we plug in theta p. We can solve for mm and m of n. All right. And then we can use the transformation equations again to plug in our values of y and z here to solve for the values, our coordinates m and n for m and n. Okay. So if we do that, we'll get these values for m and n. Okay. Now we have all the terms necessary to solve for our stress at a point m and n. Okay. So we have our moment of inertias about the m and n axis, and we have the point in the coordinates m and n. So if we plug in so basically all of our values are known. We can now just plug in our values that we have solved for, and we can solve for the stress at that point. Okay. And you can do the same thing at the opposite end of our beam. All right, so we just solved for the stress here. stress at the other side of the beam, we solved for it to be the opposite, equal opposite stress would be minus 63.4. Okay. Now, if you had just gone along and had decided to use the traditional beam theory where you just say that my moment is going to be equal to the moment about the z-axis times y divided by iz, and you plugged in those values, you would have estimated the stress to be 206 megapascals, which is very different from the actual stress that was calculated to be 63.4. It's almost, it's a little bit more than 3 times as much of stress. So it's very important for these axisymmetric problems that you do, or for these unsymmetric bending problems, that you do use the unsymmetric bending equations. Otherwise, your estimates for the stresses within the sections are going to be very different from the actual stresses experienced.